So first of all, thanks for having me here. I'm RC. I graduated from Columbia last year, and I'm at Shanghai Jiao Tong University right now. So I'm going to do today is I'm going to present a decision theoretic work. I'm going to give a short version of it. Instead of going through the proofs, I'm going to focus on the key idea. And I might end up omitting some important technical details for you. I apologize for that in advance. So, to start off, I want to, sort of categorize the decades worth of evidence that we collected on choice data into, if I may, two strands of non-standard behavior separated by a line. The first one, you must have heard of it, they're warp violations. So these are behavior that is not consistent with the maximization of a single utility function. And these are behaviors that is not consistent with the maximization of a single and stable preference relation. It's very annoying because essentially it's an assumption that we all make doing economics research for a very long time. And the behavior that is in direct contradiction to that assumption of rationality is behavior that looks like this, right? Where an individual would choose X over Y in some choice set, but then Y over X in another choice set. But then there's sort of a completely different strand, if I may, that I call structural violations. So these are individuals that do not necessarily violate the weak axiom of rebuilt preferences. They may still be characterized by the maximization of a single utility function. It's just that these utility functions or preferences do not necessarily have the structure that we typically assume. So some examples are in the risk choice over risky prospects domain. We have the well-known LA paradox. These are violations of the independence axiom, and the guy therefore cannot be represented by an expected utility maximization. In the time domain, there is a present bias of dynamic inconsistency, and therefore the guy violates the stationarity axiom, and therefore he cannot be represented by exponential discounting. In social domain, people are not fully selfish. It turns out that they care about other people, and there's inequality aversion. So they do these two strands of non-standard behavior. And in response to each strand, there are lots of work that were done sort of to capture each strand in isolation of another. So you have heard of all these models. There are a lot more. I'm just listing some of them, presumably the older ones. For warp violations, there's a decoy effect, there's endowment, status quo. And for each of these structural violations, you have probability weighting, disappointment aversion, rank dependent for the risk domain. You have quasi-hyperbolic discounting for time domain, and you have all kinds of different utility models that capture inequality aversion in the social domain. So the key takeaway here is that I think for the most part, we have had these two different types of non-standard behavior, and we have dealt with them in isolation of one another. It is a good economist thing to do so. We weaken one thing and we keep everything else the same. But what I want to do today is to sort of try to understand them together. So what I want to do today is to present a work that attempts to study how warp violations and structural violations may in fact be related to one another by using a unifying framework. And if I'm successful at it, then this framework should achieve a few things. The first thing is that it should work across choice domains, right? It should not be something that is very specific about warp violation and the independence axiom. It should be something that is about that works for the risk domain, time domain, social preference domain, etc. This framework should also have a common structure. I'm going to be presenting a number of models today that came out of this framework. But essentially, the idea is that they should have similar models and similar axioms, and therefore they are within the same framework. So, this unifying framework that I'm going to propose today is built on a rather unsophisticated observation, I think. And that is, if you imagine a guy having set-dependent utility functions, then even if he then proceeds to maximizing expected utility, his overall behavior is going to end up violating both warp, because he's maximizing different objective functions from time to time, and as well as independence. But the component in which he is actually maximizing the expectation of some utility function, even though these utility functions are changing, also leads to the simple observation that whenever if you manage to find the times in which this guy has a fixed utility function, then behavior would lead to compliance with both warp and independence. So I will capture this general idea and apply it to various domains. Essentially, what the unified framework that I will propose is going to capture set-dependent utilities The way I'm going to do that is I'm going to introduce a template that takes a model and spits out a weakened version of the model on both the axiom side and the representation side. And I will show that, just by doing that, it's going to provide some natural explanations for the structural violations that we observe in the race, time, and social domain. The reason for that is that in this word that I'm introducing, warp and structural violations are going to end up as studied as stemming from a common source. And one thing that I would not be able to go through much today, but very much the key of this project is that this approach is going to hopefully allow us to study non-standard behavior across domains as related to one another. Okay, so let's quickly go through the most general model in which the guy is just choosing between alternatives. Everything in the talk today is going to be centered around this axiom, right? You can think of it as serving as a template for all of the axioms that will come later. So let's read this axiom and I'll give you an example next. So the axiom says that for every choice set A, there exists an alternative in this choice set, such that if I look at all of the subsets of this choice set itself, and I look at the corresponding choices from this subset, they are going to satisfy warp. Okay, so put it differently, what this axiom is saying is that warp may not hold in general, but it holds in the presence of some alternative X when you take subsets. Now, of course, this axiom is going to hold trivially if your choice correspondence satisfies warp everywhere. Now, when it does not satisfy warp everywhere, this axiom may still hold, as illustrated by the following example. So what I'm going to do next is I'm going to show you this one choice correspondence, and it's going to stay on the screen for multiple slides, and I will show why this axiom holds here. So, for notation, I'm displaying this as, a choice set containing A, B, C, D, and I use underline to denote the choice. And therefore, this is a fully defined choice correspondence when your set of alternatives is A, B, C, D, right? And I'm going to start pointing out the warp violations in this slide. So this is one pair of warp violation. The guy chooses B over C in one choice set, but then C over B in another one. This is a second pair of warp violation, and this is a third pair of warp violation. And therefore, this choice correspondence does not satisfy warp because it violates it 3 times. Now, going back to the axiom says that if I pick one of these 4 guys, A, B, C, D, and I consider all of these sets that contains that alternative, I can dodge all of the warp violations. It turns out that you can do so if you select all of the choice sets that contains A, right? So if I just look at all of the choice sets that contains A, so in particular the ones that are highlighted in blue, then if you rewind your memory by 2 seconds, you remember that all of the warp violations that existed, for example, between these 2 guys and between this guy and this guy, none of the pairs are included in this selection. And therefore, this is what I mean when I say that the choice correspondence is going to satisfy warp when you select subsets by fixing an alternative. In this case, that alternative is A. Okay, so this is just to quickly show you that this axiom has a bite. You can't always do this with just any choice correspondence. So this is another choice correspondence. It is the guy chooses B from ABC, A from AB, C from CB, and A from AC. And I'm highlighting, I'm copy pasting this choice correspondence here, and I'm highlighting a warp violation. There's one between this first and second choice set, and there's another one between first and third one. And one way to see that the axiom fails is by going through each of the alternative in ABC and showing that no matter which alternative I pick, I would end up highlighting choice sets that contains a warp violation. If I choose A, I would select these 3 choice sets, and remember one warp violation occurs between these 2. If I select B, I would end up selecting this, and there's a warp violation. If I select C, there's a warp violation, right? So this axiom has bite. Okay, and just with that one axiom, you can have the following representation. The guy, this choice correspondent admits a representation in which there is a complete and transitive and antisymmetric order R, it's also called a linear order, over the alternatives. And he also has a set of utility functions. Each one is indexed by an alternative. And what the guy does, so how is the guy going to use these parameters? What the guy does is that when he faces a choice set A, what he's going to do is he's first going to look at
until question.
Thank you. What he's going to do is he's going to look at the reference order, the order R, and he's going to pick the guy in the choice set A that maximizes this reference order. Remember, because it's complete, transitive, and anti-symmetric, there is a solution for every finite choice set, and it's unique. So it's going to pick the reference alternative, essentially, of choice set A, and then he's going to look at a utility function that is indexed by that alternative, and he will maximize that. So once the reference point is pinned down, and it's pinned down by the maximization of a linear order, the guy is completely normal in the sense that he maximizes utility. So this is the most general model. What we want to do with that is, I want to show you that this template, this axiom one, actually can be adapted to different situations to capture essentially the same idea, but then now instead of the guy being completely normal after fixing a reference point, the guy is additionally also completely normal in terms of expected utility maximization after you fix a reference alternative. So in the risk domain, this is the axiom that I showed just now, right? For every choice set A, there is an alternative such that if you pick out all of the subsets of A that contains that alternative, warp is satisfied. What I'm going to do now for the risk domain is to introduce R1. And I'm highlighting all of the differences from A1 to R1 in blue. It says that for every choice set A, there is a safest alternative P such that C is going to satisfy warp and independence instead of just warp itself over the set of all subsets of A that contains P. I omit the definitions of these two. Definition of independence is just standard, it's in the paper. Safest is a bit more involved, it's also in the paper. There's a second axiom. The second axiom says, simply, let's just, in essence of time, it simply says that, when choice set expands from A to B, and that therefore B is a superset of A, choices are more risk averse. In reality, I think what this writes here is that choices are not more risk loving, because if you choose a convex combination of delta over a convex combination of P, you would not reverse your choice, which is how it's typically defined in Rubinstein's textbook, for example, as being more risk loving. Okay, so with these two axioms, I'm going to show you the utility representation. So this is what you had before for the most general case in which the guy is just choosing between alternatives. And what you have now with R1 and R2 and some technical axioms, namely continuity and stochastic dominance, the guy is going to have, instead of a utility function, he's going to have a set of Bernoulli utility functions. Instead of a reference order, he's going to have a risk reference order that captures what is the risky thing in the choice set. And the way he makes decision is that every time he faces a choice set A, he's going to maximize this risk reference order R to find the safest alternative in it. And once he identifies what is the safest alternative, he's going to maximize the expectation of the utility function indexed by that safest alternative. So in other words, this guy is a completely standard expected utility maximizer. He does this operation of taking expectation of things and maximizing that with respect to some utility function, except that this utility function changes from time to time, and it's determined by some ordered reference. So there's another property that comes out of this to govern how preferences do change when utility functions change. And that is if your reference point P is safer than your reference point Q, then the utility function that you use under P is going to be a concave transformation of the utility function you use under Q. So in other words, we are describing the following story. We're saying that look, how averse you are to risk, in some sense, depends on whether it could have been avoided in the underlying choice set. And that avoidability is characterized by the safest option that is available to you in this choice set. If you can avoid risk, you end up behaving in a more risk-averse way in terms of, and that is captured by using a more concave utility function. There's some evidence of this. I will skip that a bit. Okay. Now I'm going to do the same thing with, let me go through this a bit. So, just to illustrate that model a bit more, I'm going to take this LA paradox. I know there are tons of explanations to that, but hear me out. So in my model, the way LA paradox is explained, first of all, it does explain LA paradox, is that the safest alternative in problem 1 is safer than the safest alternative in problem 2 because it contains a shell price, for example. And therefore, the utility function the agent uses for problem 1 is going to be more concave than the utility function he uses for problem 2, capturing increased risk aversion. Once the utility functions are identified, the guy just maximizes expected utility in both choice problems, and that would explain this behavior. But on top of that, something that also comes out of this and explained in further details in the paper is that it also predicts LA paradox. in the form of a warp violation. Remember, I started off the talk talking about the connection between a warp violation and structural violation. We typically understand LA paradox as a structural violation. But if you were to consider non-binary choice sets, this paper mentions a few ways in which you can essentially see the manifestation of the LA paradox in the form of a warp violation. And essentially, you just take problem 2, you add something that makes the guy very risk-averse, and he would switch from Q prime to P prime. Okay, so now that I get that thing out, the rest is I think rather straightforward. In the time domain, look at this guy again. You're familiar with it. For every choice set A, now I'm going to choose the alternative that is the soonest payment in this choice set, and then I would say that C satisfies warp and stationarity over the subsets containing this guy. That's going to leads you to this model. The guy has a bunch instead of one. The guy has a lot of a bunch of discount factors. They're indexed by the reference. R is now a time reference order. When the guy faces a choice problem A, he's going to find the alternative that arrives soonest, and then he's going to use the discount factor that is associated to that to make choices under exponential discounting. And moreover, if the reference, and that is the soonest alternatives, arrives very soon in one choice problem relative to another, then he's going to end up using a lower discount factor capturing greater impatience. So there, I think that sort of self-explains. And finally, in social preference, we consider a case in which the axiom says that if you fix the most equal alternative in a choice problem, then behavior would satisfy both warp and quasi-linearity. We use quasi-linearity because it is about allocation of money for yourself and for the other person. The representation you get is that you have a set of utility functions that capture your other regarding utility. And then R is the equality reference order. In this case, it's actually a Gini coefficient. So what you do is when you face a choice set, you find out what is the lowest Gini coefficient, which captures equality. And then you use the corresponding other regarding utility associated to that Gini coefficient. When your Gini coefficient is very low, and that is attainable equality is very high, you're more willing to share. So sort of like a social allocation problem that if I could share more, then I would end up sharing more, even if that might cause me to violate the weak axiom. Okay, so now I have 2 final notes for the last 2 minutes. So I will go a bit slower here. So essentially, what this framework is doing is that it is providing a template, right, for us to take a model, a standard model, expected utility, exponential discounting, etc., and it's going to spit out a reference-dependent version of this model. Now, so this is the axiom. Essentially, I generalize as that in the appendix. I think it was supposed to be in the body, but referees preferred it's in the appendix. So I write down a template. The template says that for every choice set A, there is an alternative in some subsets of A that you can customize, and then that the choice correspondence satisfies both warp and some arbitrary properties. I tried independence, stationarity, quasi-linearity over subset that contains that alternative. So in other words, what this unifying framework is actually manifested as an axiom that weakens other axioms to capture reference dependence. Now the last point I'll brief through is that in each of these models, we know that utility representation and warp implies each other. That is just a general fact. It turns out that in these models, if you have warp, then you would also have the structural property. So this is a result. And therefore, if you have warp and the structural property, you also have the original model. So in the sense, this warp, the weakening of warp and the weakening of independence are actually inextricably linked, because if you compensate the model with either one of them, then you go back to standard model. And therefore, it is a mapping that, in fact, people are violating expected utility because they are violating utility representation to begin with. Okay, so let me conclude. What I've done here is I presented to you a unifying framework. It is a template that for set and reference dependent preferences. It is one way. There may be other ways out there to study warp and structural violations as related, and therefore it provides some new empirical ideas for link between anomalies. It guides you as to some new experiments that I hope people do and I will do to test between these anomalies. And on the modeling side, what this work is doing is that for a fixed reference, you would have standard theory, right? Once you fix your reference point across choice sets, then the guy is expected utility, it's exponential discounting, etc. The benefit of doing that is that now you're able to use the original axioms, as you see them popping up in the axioms that I presented today, to be the foundation of these models. And another thing I didn't go through is that this allows you to model changes in preferences with known technology. If you remember, utility functions are related by concave transformation to characterize increased risk aversion, discount factors that are higher and lower to characterize increased patience, etc. It's a rather simple way of modeling changes in preferences. And lastly, the reason we are able to do this is because we are working with choice correspondence instead of preference relations. It's important because, in preference relation, you either have independence or you don't have independence. There's no way to have a partial independence, but with choice correspondence, you could, only if you also have WALP violations. So I think this opportunity really comes from us living in a world in which we know that people violate WALP. We also know that they violate structural postulates. So instead of sort of like explaining one in isolation of the other, if we could just accept both of them as facts, then we could do a lot more. That's the end of my talk. That is my email address, the link to the paper. Thanks so much.
Very good. Thank you, RC. Very nice. We still have 4 minutes, 3 minutes for questions. So we're gonna open the floor and see if there are questions. It's very elegant. Let's see if we have
I have a question. Yes.
Yes, go ahead.
Hi, it was a very good talk. It looks really amazing. I have one question, which is about continuity. So I was curious what's going to happen if the choice set is continuous or infinite. And my sense is that in the standard framework, you would still want warp to hold like for all alternatives. But it seems in your framework, the requirement you put is just so that it only holds for one alternative. And so I'm wondering that with continuity, does that imply that, or does that basically make your framework less testable empirically? Is that something?
So first of all, there are two ways in which we can think about infiniteness in this case. One is the grand set of alternatives being infinite, and another one is the choice sets themselves being potentially infinite, right? So the model does itself capture, allow for the grand set of alternatives being infinite, but it actually is only restricting attention to choice sets that are themselves finite. If you remember, there is this R thing that the guy needs to first maximize, right? If the set is not, if a choice set that he may potentially face is not finite, then the R need not have a solution unless you endow the R with some continuity property, which I honestly do not know how to do in this case, unfortunately. The construction, we are sort of like constructing two types of objective functions here, right? One is the R that the guy first maximized, and then you have the utility function that they maximize after they find out who are the reference points. And essentially, it is because of this two-step process that makes it such that if you just impose continuity on the entire choice correspondence, there is still no way for you to guarantee that R itself is going to end up being continuous. So I'm not sure if that makes sense. It might be a bit of a subtle point for me to make in such a short amount of time. But essentially, I do not know what happens if you want to allow for choice sets that are infinite themselves, but we do allow for the grand set of alternatives being infinite. In fact, we have to, because the grand set of alternatives in the risk domain is infinite, right? All the set of all convex combinations of prices.
Okay, that makes sense. Thank you.
All right, so thank you for being here. This talk is about risk preferences across categories, theory, and evidence. It's joint work with Carrie Deck at UA and Patrick Dejanet at Waseda University in Japan. So monetary lotteries have been the workhorse framework for understanding decisions under risk for a very long time, over half a century. However, many choices in real life involve uncertainty about non-monetary outcomes or about multidimensional outcomes. So in this paper, we investigate risky choices between multidimensional outcomes. Our approach is to generalize the salience theory of Guardalo, Geniali, and Schleifer, 2012. We then apply this generalization, which we call categorical salience theory, to explain recent documented empirical puzzles involving multidimensional outcomes. We then test a novel prediction of this model in a new experiment, and then we close by applying the model to explain empirical puzzles in consumer choice and contract theory. Recent studies have tested whether people treat multidimensional risky choices the same as unidimensional monetary lotteries, and have found systematic differences. In particular, revealed preferences over consumer goods appear to be less risk averse and more consistent with expected utility theory than revealed preferences over monetary lotteries. And we'll get to both of these findings by Desjardins and Aurelius Calvera in a bit, in a few slides. In applications in the consumer choice literature, Simonson 1990 and Reed and Lowenstein observed greater variety-seeking behavior when participants chose a combination of alternatives simultaneously and when participants made their choices sequentially. In insurance application, Johnson et al. Observed greater willingness to pay for categorized insurance than for comprehensive insurance. Seems there's also a greater demand based on the market for categorized insurance. An example would be a greater demand for flood or earthquake insurance combined than for natural disaster insurance. Choi and Presley, 2016, find in an experimental study that non-monetary incentives can be very effective at incentivizing effort, and that task performance increases the more participants categorize performance contingent pay separately from salary. So we introduce a generalization of salience theory, which provides an explanation for each of these effects. So there's a very large literature on context-dependent models and choice in decision-making. I can't review them all here. I'll just talk about the ones that are most related. The two most related are really regret theory and salience theory. Fabian Herwig and co-authors have recently shown that salience theory is formally a special case of regret theory. In that sense, our generalization could alternatively be called categorical regret theory, but we think that the intuition for our approach more closely aligns with the salience interpretation. Leland et al. 2019 developed an alternative salience model that applies to risk, time, and uncertainty. Landry and Webb developed a context-dependent model of consumer choice, which is based on a mechanism from computational neuroscience called divisive normalization. We show the relation for this is that we show that in our paper that the salience function used by Bordalo, Giunielli, and Schleifer can be linked to a measure of visual contrast, also used in computational neuroscience. So there is room for potentially deeper foundations for salience theory and for our generalization. So as a brief overview of salience theory, it's proposed by Bordalo, Giunielli, and Schleifer in a QJE paper in 2012. In that model, the decision maker is posited to engage in a two-step process. First, pairs of payoffs are ordered by a salience function into salient states. Second, less salient states are discounted by a constant discount factor, similar to how distant time periods are discounted in standard models of intertemporal choice. Okay. Lottery L1 is then chosen over lottery L2, given the choice set, if and only if the sum of the difference in utilities in each state between payoffs from L1 and L2, weighted by both the salient discount factor for the salient state and the true probability of the state is positive. So if the salience weights and the true probability weights correspond to a greater value for lottery 1 relative to lottery 2. And Bordalo, Giunielli, and Schleifer assumed that the decision maker perceives lotteries as statistically independent, and they assumed the minimal state space that arises from this perception of statistically independent lotteries. Yeah. So in our generalization, in our approach, we assume that the outcomes are grouped into different categories. From a cognitive science perspective, categorization is a natural and pervasive cognitive process. One general article on categorization and cognition goes so far as to say that cognition is categorization. I won't go much into the technical details on this slide, but the model can be explained more intuitively by we'll illustrate how it works in some specific examples. Formally, our approach departs from standard salience theory in two respects. First, we collapse the salience ranking and choice stages into a single decision stage in which the salience weights are directly applied to utility differences. Right? So instead of there being a salience ranking over states, the salience weights are directly applying to these differences. This allows for a continuous change in the salience weights rather than a discrete change. But this difference could also be made within the bounds of the standard salience theory. Our main novelty is to assume that outcomes are aligned by their categories rather than by their states. This seems to us to be a plausible or even a natural assumption, given the fundamental role of categorization in cognition. An advantage of this approach is that for any given set of categories, our approach adds no new parameters to the standard salience theory model. And so moreover, our approach reduces to standard salience theory when there is only one category. Within categories, we adopt the minimal state space of Brodal, genealogy, and Schleifer so that lotteries over outcomes within the same category conform to the standard salience theory. So first there's the summation within categories and then the summation taken across categories. In terms of the properties for salience function, for the salience function sigma, we use the same properties that Brodal, genealogy, and Schleifer assume. They assume ordering in diminishing absence sensitivity explicitly in their salience function definition. Intuitively, ordering implies that the perceptual system is more sensitive to a difference between $10 and $50 than to a difference between $20 and $30. DAS implies that the perceptual system is more sensitive to a difference between $1 and $100 than to a difference between 101 and 200. So DAS states that for a fixed absolute difference, perception is more sensitive to larger ratios. IPS states for a fixed ratio, perception is more sensitive to larger absolute differences. So it would imply that a difference between $1,000 and $2,000 is more salient than a difference between $10 and $20. Okay, so these are the psychological assumptions underlying the salience function. And the salience function we use in our specific illustrations is the one used by Brodal, genealogy, and Schleifer. This theta parameter is greater than 0. When theta is greater than 0, this function satisfies ordering, DAS, and IPS. It's related to computational neuroscience in the following sense. We show in our paper that this function for the contrast between two payoffs in a choice set, exactly the same functional form is used in a measure of visual contrast in computational neuroscience to model the contrast between 2 pixels in an image. So there may be rooms for deeper links between salience theory and decision making and other forms of other aspects of cognition. Throughout, we simplify we use a very simple parameter setting. We set theta equal to 1. We set utility to be linear. The precise value of theta is not particularly important. For a wide range of parameter values, theta greater than 0, the results continue to hold. Okay, so Diderot found that choices are more risk averse for money than for choices over consumer goods. Now, under our categorization structure for this categorical salience theory, this is essentially how the choice gets framed or represented. For a choice between for a coin flip between the monetary lotteries, one that offers $15 or $5, another that offers $10. What was that?
10 minutes.
10 minutes. Okay. Thank you. One that offers 50-50 chance of $15 or $5 versus $10 with certainty. The salient comparison here by diminishing sensitivity is with the $5 outcome and the $10 outcome. As this is more salient than the incremental gain of $5, salience theory predicts risk aversion in this case. So the categorical salience theory also predicts risk aversion in this case. In this setting where there are lotteries over multiple goods, and so essentially the lotteries the goods are each their own category, then the comparison between 15 and 0 becomes salient, which isn't a comparison that is cued in the within category, the monetary frame. And so because of this, choices become systematically more risk-seeking in the choice over goods frame. Now the salience weight gives greater weight to this 15-0 comparison than to the 5-0 comparison, and choices can shift towards the A prime option, generating greater risk seeking in the good stream. We can generalize that. Another prediction pertains to the common ratio effect. So the standard salience theory explanation for the common ratio effect over monetary lotteries, which we also have, is that in the choice where one outcome is certain, you have, in the choice where one outcome is certain, you can get 3Z with certainty or 4Z or 0. The 3Z 0 comparison is salient, which leads to risk aversion in the first choice. But in the second choice, using the minimal state space, the 4Z 0 comparison also becomes salient, and people shift towards risk seeking, towards the C option in the monetary frame. However, the model predicts that when choices are across categories, such as with different consumer goods, this 4Z 0 comparison becomes salient. And the 4Z 0 comparison is also salient in the scaled down choice with the smaller probabilities of winning. So in that case, the model predicts that there should be no common ratio effect when the goods are in different categories. Moreover, the effect is predicted to be specifically in the direction of a shift towards the riskier lottery, riskier option in both choices. So our Royce Calvera recently conducted an experiment. They report we manipulated object similarity by using some pairs of goods that are common characteristics, other pairs where the characteristics were more difficult to compare. We found the common ratio effect persisted for monetary consequences, but it was greatly weakened for similar goods and disappeared for dissimilar goods. The stronger tendency for people to choose the risky lottery in the scale of questions with goods may be at least partially driving this. This is consistent with our predictions and explanation for the common ratio effect over money and over goods. We conduct our own experiment to test for a within category versus a cross category prediction. So basically, we conduct a simple snack choice experiment. People choose either between choices involving the same snack, one or two of the same snack, versus choices between different snacks. And the model predicts that under our calibration, the model predicts that choices will be choices across categories are going to be more risk averse in the within category choice than in the cross category choice. So when choosing between different snacks, the prediction people will choose, be more likely to choose the riskier lottery. So the choices are essentially between a 90% chance of one snack, or a 50% chance of two snacks, or 90% chance of two snacks, or a 90% chance of one snack, or a 50% chance of two snacks. Okay, so we gave subjects a consent form. This was conducted on the University of Alabama campus. We strolled around a shop cart with the different snacks around the green. Subjects were asked for their preferred snack or their two preferred snacks based on the treatment. The selected snacks were placed in circles on the choice sheet shown on the next slide. Subjects were informed that they had to select between choice 1 or choice 2. Subject rolled the die. They received the snack based upon their choice and the outcome of the rolled die, and they were dismissed. So in the treatment where there was just they would pick their two preferred snacks. It would either be two of the same snack or two different snacks, depending on the treatment. We'd put the snacks on the circles. They would roll the die. They would make their choice of either 90% chance for one snack or a 50% chance of two snacks. And these were the snacks that we used in the experiment. All roughly cost about the same.
As a 5.
Yep. Okay, and then so we found that, not a large effect. We anticipated we had 154 subjects. We do observe a significant effect. Basically, the directional prediction of the model is that choices in the cross-category choice will be more risk-seeking. We do observe that. It is significant at the 5% level for a one-tail test, which is what we are essentially anticipating because we only collected data to yield 80% power for identifying the 5% level at a one-tail test. Okay, so this was our empirical study. We also briefly apply the model to anomalies in consumer choice and in contract theory. So Reed and Lowenstein study choices between Halloween trick-or-treaters, and they find greater variety seeking and simultaneous choice. The children trick-or-treating are essentially choosing their portfolio. They can, in the simultaneous choice, they can choose one of each candy, or two of one candy and none of the other. In the sequential choice treatment, the children can only choose one candy at a time across 2 different houses. And these were the same candy. This was, I think, one was Snickers, one was Milky Way. They found that in the simultaneous choice, people are much more likely to choose one of each. And the sequential choice, they got about no difference. So it's about 50-50 for each choice. This is predicted by the categorical salience theory. In the simultaneous choice, the 1-0 is more salient than the 1-2 comparison based on diminishing sensitivity, which predicts the preference for the diversification heuristic, one of each. But in the sequential choice, neither option is more salient than the other. In the contract, for the contract theory, for the contract theory application, there are findings that people are sensitive to both are also sensitive to non-monetary to non-monetary incentives in contracts. In practice, employment contracts often feature non-monetary incentives, such as a bonus paid vacation for good performance. A field experiment by Lockwood 2010 found a contingent time off plan that rewarded high productivity with paid time off led to an increase in productivity that persisted 6 months after the initial intervention. From the perspective of neoclassical economics, monetary incentives should dominate non-monetary incentives of equivalent value because money has option value. Employers may not know how employees preference maximizing choice for how to use that money. From the perspective of our model, non-monetary incentives provide another category of outcome in addition to wages, which due to diminishing sensitivity of salience perception, could incentivize agents to work even for more than for a marginally higher wage. So the benefit of when you categorize the payouts differently, you get this comparison between the bonus for the paid time off is more salient than an incremental higher wage, and that can lead to a more inducing more effort for these non-monetary incentives. In an experiment, Choi and Presley confirmed this prediction. They find performance increases, more participants categorize performance contingent pay separately from salary. Okay. And so to conclude, we introduced the categorical salience model, which generalizes salience theory to multidimensional outcomes, in which outcomes are aligned by their categories. The simple specification provides unified explanation for greater risk aversion over money than over goods, common ratio effect for money but not for goods, greater variety seeking and simultaneous and sequential choice. We didn't cover this one, but greater demand for categorized and for comprehensive insurance, effectiveness of non-monetary incentives. And a new experiment, we found support for the CST prediction of greater risk aversion for within category. 1 minute?
1 minute, yes.
1 minute, a greater risk aversion for within category than for cross-category choices. The original salience theory was constructed primarily to provide an alternative explanation for anomalies that prospect theory already explains. Our approach takes salience theory to anomalies that are not explained by prospect theory or the other leading models of choice and risk. So we'll conclude there. Thank you very much.
Okay, thank you, Mark. Thanks, very nice. And we have now 5 minutes for questions. If anyone has questions, then it's a good time to ask. Mark, if we don't have direct question, if you have something you want to add, that's another option. You know, we can talk about more applications or.
Sure. So the
But just a minute, let's wait another 5 seconds if there's no.
Sure, no problem.
Okay, so the floor is yours. If you want to say something additional, of course you don't have to, but if you want to talk about applications.
Yeah, no, I think I won't say much more at this time. I think we covered the main points.
Well, let me just clarify it. The Salience theory helped you because you cannot do what you do with. So what was the benefit from? So use a Salience theory in a different way than it's typically used. Can you explain that a little bit more? What was the
Sure. So Salience theory traditionally ranks ranks states based on ranks outcomes based on salient states, right? So choices between individual outcomes.
And Jason, for people who are not familiar with salience theory, so what's determined the salience?
So okay, so salience. Okay, so in this representation, salience is determined by the comparison of payoffs within each category.
Oh, I see.
So they can illustrate it more clearly here. So they use the minimal state space. So the state space viewing these two lotteries as statistically independent. So this lottery is a 20% chance of 4Z versus a 25% chance of 3Z. This is how salience theory represents this choice. We show that if the alternatives are aligned by their categories, such that you perceive the diminishing sensitivity property within each category. So this becomes the lottery then if you view it as a lottery over good 1, a lottery over good 2. And if you just align the outcomes by the categories, you get systematically different predictions, and they accord with some of the recent experimental results. So that's essentially the main substantive difference, is that outcomes are aligned based on categories rather than by their salient states. Within categories, we use the minimal state space that Pradalo and Gianelli and Schleifer use.
Okay, thanks. We have another 2 minutes until the last talk. So if there is more, if you have more to say or some more question, we can do. But I'm going to start only in 2 minutes. Okay, so thank you, Mark. This was very nice.
Thank you.
I'm going to clap for everybody. Is RC still?
Yes, I'm still here.
Still, yeah. So it's 3 o'clock in the morning in your time, but you're going to take time for me.
Yes.
I'm going to start in 40 seconds, but maybe I'll share. Will you stop? So do you want to? This will stop screen sharing for Mark. Okay, yes. Now I'm going to share my screen. Let's see if I can do that. Okay, and I will start in exactly in time in 10 seconds. Okay. Okay, so I'm gonna. I don't see myself. Just a minute. Let's see if it's okay. No, I see myself. Okay, so thank you for staying for my talk, and this will be the last talk of the session. My name is Ido Erev, and I will present a paper with Eyal Ert, Uri Plonsky, and Yafim Roth. As you know, and the paper is about 6 contradicting deviation from rational choice and the impact of experience. As you know, classical decision research try to facilitate the prediction of choice behavior, just a minute, by identifying a robust deviation from the basic rational model and develop generalization of this model that can capture this deviation. For example, Kalman-Tversky had assumption to capture loss aversion and overweighting for event to the rational model. And Indira had assumption about simplicity. And so all the talk we heard now use this approach. It has a lot of nice feature, but in our talk we want to show a shortcoming of this popular method and propose an alternative method. The shortcomings that we present, that we want to show, is a result of the fact that deviations are not robust. There are many, for example, changing the correlation between the different outcome change behaviors that looks like loss aversion to the opposite direction, going to look like gain seeking. And the alternative approach that we're going to propose focus on the impact of experience. Okay, just a minute. Okay, so our previous research highlight large difference between decision from description and decision from experience. All the talk until now in this session, I think, focus on decision from description. In decision from description, people behave as if they overweight a rare event, but experience reverses this bias. Here's an example. In one of the experiments we ran, subjects were asked to choose between a safe prospect that led to a loss of 1 shekel with certainty, or a risky prospect that led to a loss of 20 in 5% of the trials and 0 otherwise. Initially, they just showed that gamble like this was described and had to select without any experience. And then we get the pattern predicted more or less in the direction predicted by prospect theory, that people should not like this gamble, also by simplicity theory. So initially, they don't like this gamble. Select it only 48% of the time. But if they play it repeatedly and they get feedback after each trial, despite the fact that we're only going to pay them for 1 randomly selected trial after 25 trials, then after a few trials, the subjects start behaving as if they like this lottery. So initially, they exhibit high sensitivity to a rare loss of 20, but after a few trials, they behave as if they believe that it won't happen to me, and they actually like this gamble. So they violate, so they deviate, they behave as a risk seeker in this example. The current paper extends this investigation and show that experience can trigger not only this deviation from rational choice, but it's trigger 6 pair of conflicting deviation from maximization. And even when we do not study the impact of description, so we go beyond the description experience gap. Okay, the starting point of our analysis is observation that come from our previous research, that the main impact of experience can be captured with the hypothesis that people tend to select the options that have led to the best average payoff in a small sample of similar situation in the past. Importantly, this is not because of cognitive limitation. To clarify this point, think what you would do in this experiment. In trial 16 of this experiment. In the first 15 trials of this experiment, so basically in each trial of this experiment, you have to choose between up and down. In the first 15 trials, down always maintains the status quo, so you got 0. Up led to a loss of -1 in most trials, but in some trials led to a gain of 2. So what would you do in trial number 16? What our subject do, despite the fact that on average up led to a loss, they select top in trial 16. Most subjects select top, and I think most of you would do the same. And the reason is, according to our theory, is that people do what works in similar situations in the past. And trial number 16 looks similar to trial 12, 8, and 4. They are similar because in both cases, this trial come, in all these 3 cases, and also in trial 16, this trial come after 3 trials in which top led to a loss of -1. So basically what subjects are doing, they do what works in similar situations in the past, and this strategy approximates the optimal strategy when the environment is dynamic. But when the environment is not dynamic, this behavior can lead to deviation from maximization. And I would like to argue that many of the deviations that we see in real life can be explained by this simple idea, that subjects are not stupid, are not cognitively limited, but the brain tries to find pattern to respond to dynamic world. And when the environment is not dynamic enough, then it can lead to deviation from maximization. Our paper focused on 6 pair of deviations, of contradicting deviation of this type, but I will focus in this talk only on 2. The first one, basically I'll focus on 2 observations. I first will show that the reliance on small sample hypothesis that I just described implies bimodal reaction to rare events, and that can be consequential, for example, like the coexistence of some people that respond in panic to the risk of COVID-19 and many other people that behave as if it won't happen to me, and these guys help spread the virus. The second observation that I'll try to argue that reliance on small samples imply non-monotonic risk and loss attitude. And that will be similar to real-life phenomena, like, for example, the fact that many people are underinvested in the stock market and behave as if they are loss-averse or extreme risk-averse. But the same people, some of them, take crazy loan to buy real estate, and which imply much higher risk if they would study economics carefully enough. Okay, so although the motivation is real-life phenomena, we're gonna examine behavior in a very simple experimental paradigm, and this is the experimental paradigm. Most of our experiments were run in the internet using Enter, and when the subject log into the experiment, they see the following screen. They're basically being told, the current experiments include many trials. Your task in each trial is to click on one of the 2 keys presented on the screen, and we tell them, each click will be followed with a presentation of the key's payoff. Your payoff for the trial is a payoff of the selected key. We use different final incentives. Sometimes we pay for one randomly selected trial. Sometimes the payoff for our lottery ticket, and basically the more they earn, the higher probability of getting bonus, but we don't get a big difference between the different experimental methods. So for example, if the subject select in this trial right, I just selected right, and then it tells me, you selected right, your payoff in this trial is 1. Had you selected left, you would get 0. So after each trial, the subject gets full feedback. Okay, but a priori, they don't, unlike the example I presented before, in this experiment, we don't give them any description. They have to learn from experience, just as we learn from experience how to respond to COVID-19. So here I choose again, and I get this payoff. Okay, so here are now, so hopefully you understand the experimental paradigm, and I want now to show you these 2 pair of results. The first pair involves the impact of rare events. Look at the dark condition here. In this condition, now each one of my condition will run for 100 trial. And in this experiment, subjects have to choose between 0 for sure, or a gamble with negative expected values that lead to a loss of 10 in 10% of the time, and lead to a gain of 1 otherwise. So the expected value is negative, minus 0.1. What we see that in this condition, subjects select the bad lottery initially 70% of the time and experience reduce it to 60% of the time, but it's never go below 50%. So they continue to select this bad lottery and behave as if it won't happen to me 60% of the time. In the light condition, as a lottery has positive expected value, it's a lead to a gain of 10 in 10% of the time, minus 1 otherwise, and positive expected value, but the subject selected only 32% of the time. That is, in both conditions, they deviate from maximization in the direction of underweighting of rare event, which is exactly the opposite of the prediction of prospect theory that implies overweighting of rare event.
10 minutes left.
Notice that, and here on the right-hand side, you see a model, a simple model of this reliance on small sample hypothesis. Basically, this model here assumes that the subject rely on 5 past experiences. And it implies underweighting of rare event 2. And the reason why it selects a bad lottery here, because if you take a sample of 5, then in 60% of the sample, you will never get the minus 10 outcome because it's only 5 and it's a rare event. So if you take a sample of 5, then in 60% of the time, you say, oh, I really like this lottery. It gives me +1. All the number in my memory, in my sample, are +1. And the opposite happened here. They don't draw the +10 enough because the sample is small and they underweight a rare event. Nevertheless, the same model also predicts that in other problems, there will be a significant minority of the subjects that will behave as if they overweight a rare event and behave as if they panic, if you think about the COVID-19 example. So to see that, look at this, the light problem first. This is a trivial choice between 12 for sure and 11 for sure. And what you see here, the proportion of people select the bad prospect, 11 for sure. So less than 10% of the people select 11 over 12. And this is, even you get similar results even at the Technion, it's not only in MTurk. Some people have some reason why they think that maybe something good will happen from this 11. But now in the dark problem, we still have 12 for sure against a prospect that has expected value of 11. But this time we replace the 11 with a lottery that give 20 with probability 0.1, 10 otherwise. And this increases the probability of choosing this best prospect from 10% to 22%. This increase can be described with the assumption what the subjects are doing, they behave as if they overweight the rare event. So we get, and notice that our model captures these things too. And the reason why the model predicts this overweighting of rare event in this condition, because in a rare case, the sample does this, the average payoff from choosing the B is low, but in rare cases, you do draw the 20 in your sample, and then you feel lucky and you take it according to the model. Okay. The second set of phenomena I want to present involve the impact of losses. In this example, subjects have to select between 3 prospects. So you have 3 keys on the computer screen. One of them is a safe prospect, always gives the status quo. So 0 for sure. Second prospect is a moderate risky option with positive expected value, pay +4 with 51% of the time, -4 otherwise. And the interesting result is that people prefer the 0 for sure, the green line, over this moderate risky prospect. So people don't like the moderate risky prospect. They like the status quo more, which is consistent with loss aversion. However, notice that for some reason they like the +8, -8 even more. So there's something non-monotonic here. They like the status quo over the medium risk, but for some reason they like the high risk even more. In this experiment, in this condition here, the 4 prospects are positively correlated, the 2 risky prospects. Now in the next condition, now the 2 risky prospects are negatively correlated. When R1 pay +1, R2 pay -8, and when R2 pay +8, R2 give -4. And what we see here, we get a reversal of loss aversion. Although all the prospects have the same expected value, and prospect theory and all risk aversion will suggest that people should prefer the status quo. Of course, the status quo effect should suggest that people should select the status quo. Proportion of people selecting the status quo is only 15%. Okay, and notice that in both cases, the same model I showed you before, the model that assumes that what the subject are doing is just relying on a small sample, captures the main results. The reason why the model predicts large difference here and here is because in this situation, when you take a small sample, because the 2 risky prospects are positively correlated, R1 is never the best option, because either if you're lucky, you get more from R2, and if you're unlucky, you get more from safe. Here, when the 2 prospects are negatively correlated, safe is never the best option. One of the risky option is always better because they are negatively correlated. Okay, so basically
5 minutes left.
How much?
5 minutes.
5 minutes. Okay, thank you. Okay, so so you might think, okay, so I told you a story about this clicking paradigm, this funny experimental setting with MTurk student. How does this relate to real life? And I think it is related. I will try to convince you it is related to real life. And to show the difference between this and, for example, the prospect theory explanation of buying lottery. So according to prospect theory, people buy lottery because they're overweight rare event. But very few people buy lottery more than once a week. Most people buy lottery less than once a month. And our model can explain that. According to our model, people buy lottery. It's stupid to buy lottery, but they buy lottery when they feel lucky because they have this rare event for some reason in their sample. But in most cases, they don't buy it. So we can explain why people buy lottery without, but also explain why most of us don't buy lottery very often. Similarly, the story can explain why some people underinvest, many people are underinvested in the stock market, but why many of us still invest too much in real estate, as I showed you before, as in the previous example. I also want to clarify that the reliance on small sample is not just a post hoc explanation for the results I've just shown you. We organized 4 international choice prediction competition, and we're going to run another one on the paradigm I explained today. And in all of them, with the winning model, as a basic idea of the winning model was reliance on small sample of similar past experience. The direct implication here's the direct implication of my story. The impact of experience is large, replicable, and non-trivial. Experience does not ensure rational choice. It can reverse a deviation but it can reverse a deviation from rational choice. Yet the impact of experience can be predicted with simple and ecologically reasonable reliance on small sample hypothesis. Not because people are stupid, but because the brain is, according to our idea, is looking for patterns. Importantly, the small sample hypothesis imply very different biases in cognitive processes than the biases suggested by the common explanation, prospect theory-like models. The wider implication that I'm not sure you guys will accept them, but I believe them. To understand the wider implication, it's important to understand why we explain in our paper, we have this 6 pair of contradicting deviation. All of them were explained in previous research with different models, and we can show that we can explain all of them with one model. The question is why people ignore the fact that you can explain all of them with one model, but like different model for different phenomena. And I think the reason is that mainstream research paid too much attention to the rationality assumption. So we focus only on decision from description. Mainstream research, including the talk we heard until now in this session, focus only on decision from description because then it's easy to show that people violate rationality. And this thing led mainstream research to mask and ignore the predictable impact of experience. If we give up the demonstrating violation of rationality and try to predict choice behavior, maybe we should pay more attention to the impact of experience. This is basically my story. Do I have another minute? If
yes,
I have another,
2 minutes.
Oh, another 2 minutes. Okay, so let me show you my favorite, some of you already saw that, my favorite graphical summary of the results. I'd like to think, I take advantage that I'm the oldest person in this session, so I'm allowed to do some hand waving. I like to think about research as a hike in the land of assumptions with a hope to get to a nice point of view to look at the land of problem. So we can see what's happening in the land of problem, we can predict and maybe come up with good ideas for how to solve real life problems. And I think that what happened in decision research, that we start with expected value rule, and then we improve it a little bit with expected utility theory, and then we improve it a little bit more with cumulative prospect theory and with Salience theory and with simplicity theory, but we're all walking on the same hill and we can see a small set of the land of problem. And I think that it's maybe a good time to consider the option that there may be higher hill from which we can look at the land of problems. And maybe if we focus on different experimental paradigm, maybe we can do that. So this is basically my story. If I have some more time, I can show you how the model looks. The model is very simple. It's basically assumes some exploration and then reliance on small sample plus some weighting of the grand mean. And we plan to organize a choice prediction competition for this set of problems. And if people think that they have a better model to capture behavior in these settings, they are welcome to participate. We will send you an invitation for the competition when it will be ready. Okay, thank you.
Okay, thank you. So we're going to open up for questions for the last 4 minutes. If you can unmute yourself to ask, feel free to do so. If you cannot, type in chat or unmute you.
So can I ask a question, Ido?
Sure.
So you said you investigated 6 phenomena?
Thanks. That's a nice question because I do have a slides for it. Yes, in our paper, just a minute. Let's see. Yeah, in our paper we actually have we consider 6 phenomena, and I presented only 2 for you until now. But we show that with the same model we can also explain the coexistence of 4 other contradicting deviation. One of them is a positive and a negative effect of variability on maximization. Basically, there are many situations in which when you add variability, and this is maybe similar to what Indira's simplicity theory said, when you add variability, people basically like the prospect less, and it definitely moves them toward random choice. It confuses subject, but we also show that there are situations in which adding variability actually increases maximization, and the model can explain that this is happening. Another phenomenon that was discussed in this session is a decoys, the attraction effect. And our results show that we can explain when the decoy effect happens, but also when a reverse decoy effect happens. Similarly, there is a compromise effect, the fact that people most of the time prefer the medium option in a list. However, there are situations, and Spector et al. Show it very nice, it's in decision from experience, the common phenomenon, the opposite phenomena is even more common. And what we can show in our models that we can predict when you get the compromise effect and also the reverse compromise effect. The last phenomena that we are presenting is a coexistence of oversensitivity and also a reverse effect of taxation. We show that there are situations in which you give fine, a little bit like the Gnisi-Rostatini kindergarten example, that there are situations in which you give people a small fine for the wrong behavior, and then this behavior increases. And in our model, this is happening because in many situations, people have more than 2 options, despite the fact that mainstream research focus only on 2 and binary choice. But when you have more than 2 options, if you punish a particular behavior, for example, you punish a person that their parents arrive late to pick up their kids, maybe once you have, maybe they will start doing something else. Maybe they'll think about more strategies they can use. And in our settings, this is basically what happens. And the model predict when punishing people have backfires and when punishing is effective. So basically what I'm trying to argue is that this very simple model can explain many phenomena, but not only show that this phenomena happens, but also predict when the phenomena happen and when they are reversed.